So, yeah, I'm going to talk about making data be able to expire. So you want to be able to hold it reliably for some amount of time and then absolutely get rid of it from the storage system. So this is about the storage system. It's not about DRM in terms of if somebody were to read files on a regular computer in the clear, they could make copies, they can make printouts. That's an orthogonal problem. But the idea is that if you tell the storage system, here, I want you to store this for me, and I want you to get rid of it in 1 year, then the storage system should not have it anymore after a year. Okay, so I'm going to talk about 2 ways of doing this. One is where you give an expiration date when you create the data, and the other is where you you can say, I want to get rid of that file now, and it might take a few days, but then it will go away. Both of them are simple and practical, but the second one is a bad idea. And so one of my interests has always been distributed algorithms where some of the participants are not doing the right thing. You know, they might be malicious or confused or whatever. And so it's sort of interesting case study to look at the first thing, the design of the first thing that is super robust and sort of, allows parts of it to not be working properly. And the second thing that I'll show you is not resilient that way. So for this thing, I'm going to, for the first type, you're going to give it an expiration date. So I say, store this for me. In 1 year, I want it gone. And why would you want that? There are some countries that have some sorts of laws about what kinds of data are allowed to be kept, for how long. So, privacy data, health records or something. There are other countries that have laws about you must retain data for 3 years, but 1 day later you'd like to get rid of it so that there's sort of a limited amount of data to be searched through. So obviously what you're going to do is you're going to encrypt the data and then throw away the keys. And when you do that, you don't free up the space. So the encrypted stuff will still be there, but in a lazy fashion, you can go through and look for metadata of data that has expired and then free up the space. But once you delete the key, all the encrypted data is no longer readable. So that's the obvious solution, but that's not the end of the talk because it's not so simple. If you need to hold on to the keys reliably so that you don't delete it prematurely, you have to make a lot of copies of the keys. And once you make a lot of copies, it's very difficult to make sure that you can get rid of all of them. So it's not going to be quite so simple as encrypt it, throw away the keys, ta-da, we're done. So the first concept that we're going to say in order to make this thing like really manageable and scalable is that we notice that all files with the same expiration date can be encrypted with the same key, and it doesn't lose you any security to do that. If you care, by the way, that the storage system not be able to read your data, you would have an extra level of encryption, that you would encrypt it before sending it. This encryption that I'm talking about is solely to enforce the expiration time. So what you're going to do is the file system or the storage system, the cloud, I'm using the terms interchangeably just to be annoying, I guess, is that you're going to have a piece of hardware that will store secret keys, one for each expiration date. So here's the master keys. So for the January 7th key, the secret key is S1, just sort of an ordinary random number AES type key. And a file, in the metadata, it says what the expiration date is, and then the data is encrypted with S2. And when I say encrypted with S2, just because cryptographers are fussy, you wouldn't directly encrypt the data with that. Instead, you would have a random number just for this particular file. And in the metadata, you would take K, which is the random number for this file, encrypted with S2, and then the data is encrypted with K. Doing this extra level allows you to change the date of expiration and has other good properties. So how many keys are we talking about? If the granularity is an expiration date on a day boundary, which is probably, a week would probably be good enough, but let's say on a day boundary and up to 30 years, that's 10,000 keys, which is nothing. So that's, very simple. So now the question is, how do you back up the master keys? If you're going to make only a single copy of them and put it in this special hardware, so, what happens if that piece of hardware fails? Or you might even have 2 or 3 copies, but you're not going to have 100 copies. So you are going to need to make a backup of the keys, and you need to make a backup of the keys in such a way that if somebody recovers a backup from 3 years ago, they won't be able to see any of the keys in there. So how are we going to do that? To do that, I imagine a service that I call an ephemerizer. So it's a made-up word. Ephemerizer makes things ephemeral. So an ephemerizer is some sort of service that publishes public keys with expiration dates. And so a public key, since he's advertising as public keys, you can encrypt things with his public key, and he remembers the private key, and if you need him to bail you out because you need to recover the keys from backup, he can unlock the public key with which you encrypted things with his private key. So the ephemerizer says, here are my 10,000 public keys, 1 per day for the next 30 years. And just posts it someplace. So if you want to back up your master keys, and here I made up another word, you ephemerize each one. You take the January 1st key and you ephemerize it by encrypting with the ephemerizer's January 1st public key. So you take each of your 10,000 keys when you're making a backup, and you encrypt each one with the equivalent date public key of the ephemerizer, and then if you ever, and the ephemerizer promises to throw away the private key when it expires, and promises to bail you out if you need to recover your keys from backup. He won't be able to unlock keys that have expired, but the keys that haven't yet expired, he'll be able to unlock for you. So this is back to the picture of what the storage system is. In normal operation, as long as you haven't lost this piece of hardware, there's no ephemerizers. You just open the file, look at the expiration date, get the master key, and you can decrypt that file. So, but when you're making a backup of the keys, you take your January 7th key, encrypt it with the ephemerizer's January 7th key, and that's what's on the backup. And so you do that for each of your 10,000 keys, and then you wrap the whole thing one more time with some sort of permanent secret for the storage system, so if somebody stole your backup of the keys, they couldn't ask the ephemerizer to decrypt. So first I'll say how wonderfully scalable this is. A single ephemerizer only needs 10,000 keys no matter how many customers it has, because it's 1 for each expiration date. And the ephemerizer almost never has to actually talk to any of its customers. It's once every few years when you lose that piece of hardware that you might need to ask it to decrypt. So it can support hundreds of millions of customers, because all it has to do is post the public keys, everybody uses it, it has no idea who its customers are. And so, it's just a wonderfully scalable system. So, but if you think for about another 30 seconds, you're going to be annoyed at me, because all I've done is push the problem onto the ephemerizer. The ephemerizer has to reliably remember private keys and then reliably make sure that the private key is absolutely gone once it's expired. So it seems like all I've done is just move the problem one other place. But there's two ways that an ephemerizer can fail. One is where it goes out of business or forgets the private keys prematurely, and the other is where it doesn't forget the private keys. And so focus on one thing at a time. We'll get to the second one, but right now let's only think about what happens if it were to lose the keys. Because if it did, then all of its hundreds of millions of customers, when they needed it, would be very disappointed when they found out that, no, they can't recover from backup. So, so I claim that a legitimate ephemerizer, I don't want it to make any copies of the private key. So, it will generate the public-private key pairs in tamper-proof hardware, do the decryptions in that hardware, so there won't be any copies of the key. Which means that, oh gee, that seems awfully scary, because now the entire world, hundreds of millions of customers, depend on that one ephemerizer. So now, here's the kind of main point that makes this thing resilient. So first, I'll ask you, how many copies would you want the ephemerizer to make of the key in order to feel safe? So pick a number, let's say 20. And you would like it to make 20 copies of the keys, store it in different countries and whatever. Well, we don't need it to do that. We can achieve the same robustness by having the storage system use 20 independent ephemerizers, all with independent keys. So you can make it arbitrarily robust by using all these different organizations. The different organizations, different countries, different continents, and their public keys are completely independent. These ephemerizers have nothing to do with each other. So then, when you're using multiple ephemerizers, and I couldn't on this slide use 20 ephemerizers, it would get too cluttered. So in this picture, I'm only using 2 ephemerizers, but just imagine that it's 20. When you're ephemerizing, when you're making a backup of S1, instead of just encrypting it with one ephemerizer's key, you also store it encrypted with the second ephemerizer's key. So you're taking what was a trivial amount of storage before, which was 10,000 encrypted keys, and you're multiplying it by 20. And 20 times trivial is still trivial. So that's the basic concept. So you only need to talk to the ephemerizer after a disaster. Hopefully never, but maybe every 5 or 10 years. And the ephemerizer is incredibly scalable because the same number of keys, 10,000, works no matter how many customers it has. And it's very easy to build an ephemerizer. And I'll have some slides about that in a minute. So the general philosophy is that you can achieve robustness by using lots of components that are allowed to be flaky, and that it's really good to make sure that the failures are truly independent, which in this case they can be. So now, of course, everyone worries about, but what if the ephemerizer doesn't throw away the private key when it should? And for that, there are schemes known as quorum schemes, where instead of taking the S1 key and encrypting it 20 times, you instead chop it up into 20 pieces such that it requires some quorum, let's say 3, to be able to recover it. So you break it into 20 pieces, encrypt each one of the 20 pieces with a different ephemerizer's key, and then when you need to recover it, as long as 3 ephemerizers still remember the private key, then you can recover it. So it's a K out of N scheme, so you choose K and N such that you feel safe. Now, here's another piece of it that I think is kind of cool, which is the protocol for asking an ephemerizer to unlock its private key. So it's fairly straightforward. This is what we want to accomplish. So the file system has some master key, S sub I, encrypted with the ephemerizer's public key, P sub I, And what you want to do is send that encrypted bundle to the ephemerizer and say, please decrypt this with your key number I. And so he applies his private key. By the way, is the little red dot at all readable, or should I not bother trying to point to things? He applies his private key, which then he unlocks this and he can send S sub I back. So that's how you would ask him to decrypt. But the problem is you don't really want the ephemerizer to see your master key with which a bunch of data is encrypted. So that protocol itself, we want to fix it up so that the ephemerizer doesn't have to be very trusted. So because I'd like the ephemerizer to be some sort of third-party organization that you don't know terribly much about, but you certainly don't want it to see the keys with which all of your data is encrypted. So for this, we're going to use this concept known as blind decryption. Now, if you're into crypto, you've seen the concept of blind signatures, and this is basically the same sort of thing. So ordinarily, when you encrypt with one function and then you encrypt with the second function, you have to decrypt with the second function before you decrypt with the first function. Otherwise, you'll just sort of get garbled stuff. But suppose we could come up with functions where you can encrypt with one, encrypt with the second, and then decrypt with the first one while it's still encrypted with the second. And I'll show you how to do that in a minute, but for the moment, just believe that we can do it. So the second function, for some reason in the literature, it's encrypt and decrypt. It's two inverse functions, but in the literature on blind signatures, they like to call it blind and unblind. So you're going to encrypt with this function, you're going to apply the blind function, then ask the guy to decrypt, and he just applies his private key, which gets rid of the public key, but it's still encrypted with the blind function, and then when he returns the result, you can apply the inverse function, unblind, and see what he decrypted. So here's a picture of that. You have this bundle, which is S sub I encrypted with P sub I, and you invent functions blind and unblind just for this one interaction. And you say, please decrypt, and you blind this thing with key ID I, and he applies his private key. He can't tell that you blinded it. And the result is this thing, which is encrypted with the blind function. And then you can undo it, applying the unblind thing. And so the ephemerizer doesn't get to see anything. So this is super lightweight because you don't have to authenticate the ephemerizer. He gains no knowledge from it. If you're talking to the wrong thing, you'll get garbage back, but no harm done. And so you don't really have to trust the ephemerizer very much. So some people sort of need to see one example of something in order to really understand it. So I'll show you how you do blinding. I'll give you one example of it. So for you math fans, a quick overview of RSA. The RSA algorithm has a modulus n and a public exponent e and an inverse exponent d. I call them exponentiative inverses mod n, and math people get annoyed at me because there is no such term, but I ask them if they can give me a better term, and they can't. So I'm going to use it, but just realize that if you use it, people will laugh at you. But it's obvious, multiplicative inverses, everyone knows what that is. You multiply by one, multiply by the other, you get the thing back. Exponentiative inverses are where you exponentiate by one, then exponentiate by the other, and you get the original thing back. So given that E is the exponent, the public exponent, D is the private exponent. Exponentiative inverses means if you take something x, raise it to the power e, then raise it to the power d, the e's and d's cancel out. And encrypting something with a public key means that you raise it to the public exponent e, so x to the e mod n is x encrypted with the public key. So now to do blind decryption, assuming that the ephemerizer's public key is E comma N for that date, what you do is you have some sort of message M to the E mod N. It's been encrypted with his public key, and you want to have M. You want to get M back. So you choose a random number R, you encrypt it with his public key, which means you raise R to the E mod N. You multiply the two together, and you send him M to the E times R to the E, ask him to apply his private key, means he takes that to the power D, and if you remember 11th grade arithmetic, when you raise this to the power D, the exponents multiply. You'll get M to the E times D times R to the E times D. They'll cancel out, because they're exponentiative inverses, and you get back M times R mod N, and then you divide by R mod N to get the plaintext M. So, and there are other functions that work. There's really sort of only two public key things that people use, RSA and elliptic curves, and so, there's one that works with elliptic curves, but, that's not as much fun to explain. The RSA is easy to understand. So yeah, the protocol is super efficient. It takes less computation on both sides than a single SSL connection. It's a very, very tiny protocol. You can send one IP packet, get one IP response, and there's no need to authenticate either side. So, okay. So running an ephemerizer, it should be dead cheap to build one of these things. So a customer could run his own ephemerizers, but if you don't own enough different buildings, just for reliability and whatever, you may want to outsource it and use some outside organization. And then I said that the backup tape that you've ephemerized each one of the keys, you have to encrypt it one more time. And this could be as simple as kind of a sysadmin password that all of your cloud administrators know, or you can give each one of the system administrators a smart card that's biometrically activated, and it requires 3 out of 5 of them to be plugged in order to retrieve the secret. But there's many ways of doing that. So in order to retrieve from backup, you need to have stored your encrypted data someplace reliably, and you need the outer level of encryption, which I'm calling G, that's secret, and the encrypted backups of the data, and you need help from the ephemerizer. So now, after a disaster, you only need to ask the ephemerizer to unlock each of the 10,000 keys. So you need sort of 10,000 exchanges to ask him to decrypt. And that's pretty good, but you can do actually better than that. Since there's sort of no reason why the January 2nd key has to be a totally independent number from the January 1st key, you could make the January 2nd key be a one-way hash of the January 1st key, and the January 3rd key be a one-way hash of the January 2nd key. And if you don't know about one-way hashes, it's okay. You could store the January 2nd key encrypted with the January 1st key, and then store the January 3rd key encrypted with the January 2nd key. And then after a disaster, you're only going to need to ask the ephemerizer to unlock the closest to expiration key, and then you can locally derive all the rest. So once every 5 years, you have to talk to the ephemerizer to ask him to unlock one key. And this is not digital rights management. This doesn't control what happens in the client. So if a client reads a file from the cloud and is storing it unencrypted or has made a printout, this doesn't solve this. This is completely orthogonal. It doesn't make DRM easier or harder. Whatever solution you would have used for it will still work. Okay, so let's see, how am I doing on time? Pretty good. So another issue that I think is sort of interesting is how to build an ephemerizer out of dirt cheap components. So you get a smart card that's, an old smart card that has pitifully little memory on it and is ridiculously slow. and that's fine. And you get an old PC that's 15 years old that you can't use for anything else other than toxic waste, and you plug the smart card into it, and the smart card only needs to remember two things, two secret keys, the current secret key and the next secret key. And it generates public key pairs and stores them encrypted with K sub n. It stores each one, and out on the regular PC, it stores each one encrypted with K sub n. And then every time it needs to delete one, so like every day when it needs to have one expire, it will read in the, okay. So it has all of these secrets, 10,000 of them, 10,000 private keys, and it reads them all in encrypted with N. It decrypts it with K sub n, re-encrypts it with the next key, K sub n plus 1, and stores it out there, all except for the one it would like to delete. So that's every day it sort of goes through these things and gets rid of the ones it doesn't, and then once it forgets K sub n, then it's completely, the key it wanted to forget is completely gone. Let's see, a new small topic. What if laws keep changing? So let's say that there's a law saying that there's a certain kind of data that you must keep for 1 year, and then they change the law and it's now 2 years. Well, instead of having, that's another service the ephemerizer can do for you. It can keep track of all of the laws, and then the expiration date is not a time when it expires, but instead a creation date and the type of data it is. So then the ephemerizer will figure out when that key should expire. And what if you get sued? Sometimes, you get sued, and then you're not allowed to delete any of your data until the suit is over. And so the way you would do that is, in this case, you'd have to ask the ephemerizer to have one key for you. You encrypt all of your unexpired master keys with this one key, and then after the suit is settled and you're allowed to delete things again, you tell the ephemerizer to throw away that key, and then all of your previous master keys, the expiration date will be the actual time that they were supposed to go. Okay, so now I was explaining this thing to people, and people would say, oh, but I don't want to decide when I create the data what the expiration date is. I want instead to be able to point to a file and say, get rid of that file now. And so I was saying, oh, but this other thing is like so incredibly elegant and scalable, and this other one wouldn't be. And so eventually I got tired of explaining to people why it couldn't be done. And instead, I realized how to do it. And it's actually quite simple and practical and all that, but is not resilient. And it's really important to understand in what way it's not resilient, even though it kind of looks like it works. So, okay. So on-demand delete, that's where you decide this file should be gone. So, okay, I'll go straight to the picture. So what I'm going to do is that every file in your file system will be encrypted with its own secret key. And I call that F. The key for that file is F. So if you had 1 million files in your file system, you would have another data structure here that has 1 million secret keys in it. Every time you create a new file, you have to add another F into this F table. And every time you decide you want to do a short delete on a file, you remove the F from there. So now I'm going to still use ephemerizers, but before the ephemerizer didn't even have to know you were a customer. Now the ephemerizer will need to have a relationship with every customer. And for each customer, it will need to know 2 public keys, the current public key and the previous public key. So, and every once in a while, you're going to tell it throw away the previous public key, and come out with a new public key. And what you're going to do with it is, with the current public key, you're going to make snapshots of the F table. So every time you change the F table, you make a snapshot of it and encrypt it with the current public key of the ephemerizer. Every few days, you're going to make sure that you replicate this in enough different locations that you feel safe. And when you do, when you take whatever snapshot you had and it's replicated enough times, then you can tell the ephemerizer to throw away the previous public key with which the previous snapshot from like a week ago was replicated. Throw away that previous key, which makes all those old snapshots useless, and generate a new public key, and then you start making snapshots of this with the new public key. So in local storage, you have the snapshot encrypted with the current public key of the ephemerizers. Again, you could use, K out of N ephemerizers, all of that. And in the remote non-volatile storage, where you've made enough copies of it so you feel safe, it's encrypted with the previous public key of the ephemerizer. And once you've replicated this snapshot enough, you can get rid of this public key, in which case all those snapshots are gone. So, if the ephemerizer has hundreds of millions of customers, now the ephemerizer needs to know twice as many public keys as it has customers, which isn't a terrible thing. And in theory, it could just say, every week I'm going to destroy the previous public key. But I thought that was even scarier, because if you had a power failure for 2 weeks, you'd be completely, it would be, all your data would be completely gone. So if you have a relationship with the ephemerizer, you can control when he gets rid of the old private key. So what's wrong with this design? So suppose you had some sort of bug in the file system that was gradually corrupting the keys in the F table of files that you really care about but you don't look at very often. It could take you months to notice this. And once you notice it, there's nothing you can do. The whole concept of assured delete is you can only go back like 3 days. And so it doesn't help to say, gee, why is this getting corrupted? Oh, it must be after we fired Fred. Some angry system administrator that, put in malware, or when we installed this patch that was unsigned or whatever. You're absolutely, there's no recourse in that case. So that's why it's incredibly scary. Now, why isn't the predetermined expiration time as scary? And the reason is that when you use the first part of the presentation, as long as the file system was behaving properly when you created your file and it's properly backed up, it will last forever. Whereas in this thing, even though everything was great when you made copies and you replicated the copies and all that, a bug in the file system 6 months later can destroy your data. So that's sort of why it's not resilient, that you have no control over it. Some bug 6 months later means that your data is completely gone. So here's a paper in which it was published. And so, in summary, I've always been very interested in distributed algorithms that are resilient despite participants that are not quite doing the right thing. So hopefully in this talk, you've sort of seen 2 examples, one where you try to make everything very independent, and the other where, if one guy, the file system, behaves in a bad way later on, then you're really in trouble. So that's all the slides, so thank you.